There we go. All right. So we're going to create a Riemann sum. For f of x equals x squared. And we're going to use the interval from 1 to 2 and n equals 5 subintervals. And first, we'll do right intervals, or right sum. So first thing you should do is just, I always like to get a picture of what I'm doing, so quick sketch of the function. So here, I'm only going between 1 and 2, so I just want to focus on that region. So I don't really need to see much else. And let's see, if I plug in 1, I get 1. If I plug in 2, I get 4. 1, 2, 3. So that's really all I care about from the function, is that chunk there. So I'm trying to approximate that area. That's the point of the Riemann sum. So usually what I do is I just do arithmetic for it first, and then I worry about the algebra for it after. And this is kind of what I was aiming for you guys on the quiz. So first I need to figure out what my delta x is. How do I figure out delta x? Yeah, distance over how many intervals. So the distance would be 2 minus 1 over 5 subintervals. So I get 1/5. You could write that as a fraction or a decimal in this case, because the decimal is kind of nice. Then I need to take a look at my picture and break that up into my 5 subintervals. So 1, 2, 3, 4, and the right is going to be the 5th one there. And on the quiz, I only asked you to draw the right intervals. I didn't ask you to draw the left ones, because then your picture's going to get too messy. So I just wanted one drawing from you. Just to encourage you to draw pictures when you're doing these problems, because visualizing is going to help you figure it out. In this case, since the function is increasing, the right sums end up being upper sums, right? On the quiz, that function was decreasing, so the right sums ended up being what? Lower. They're going to end up being lower sums, because the rectangles are going to be underneath when it's increasing. Right. So just a quick sketch of that. If the function is decreasing, and you break it up into rectangles, and you pick the right side of the interval each time, you're always underneath if the function is decreasing. So on that quiz question, it's going to look more like this second one. All right, so let's see, I'm jumping each time by 0.2. So the first x value that I want to use, x1, that's going to be 1 plus 0.2, which is just 1.2. The second x value I need would be add another 0.2 to that, which is 1.4. Right, so I'm trying to find a pattern as I go here, because I'm going to need to write it down more generally in a minute. I'm just going to write the answer now. So the next one's going to be what, 1.6. X4 is 1.8. And X5 is just going to be 2 or 2.0. In some of the homework problems, and if you looked at the book, you may have noticed that when you're doing a right sum with 5 intervals, they would call the answer to this R with a little sub 5 underneath. That means right sum, 5 intervals. That's going to approximate the area for me. How do I find area of the rectangle? Just base times height. I'm going to write it as height times base. So when I put that area together, I'm going to switch colors, start writing it here. The first rectangle, I have to plug in its x value to figure out what its y value is. And that means I just square each of those numbers. So the height of the first rectangle is going to be 1.2. To get the y value, I have to square it. That's the height. And I multiply by the base, 0.2. So there's my height times my base. And then I just keep repeating that for each rectangle. So I've got that rectangle. Next one would be its x value, 1.4. The function says square it, multiply by the base, 0.2. And now have this next rectangle. And then I just keep repeating this. So plus 1.6 squared times 0.2 plus 1.8 squared times 0.2. And we did a problem kind of like this the other day. It was a more complicated function. You find the list of x values, you plug them in to get the heights, and you multiply by the base, and then you add them all up. What should we do next? Plug that into your calculator, get a number. Right? It's just arithmetic. You got it roughed out, so whip out your calculator, come up with a number. You should get about 2.64. I'm going to type it in. So I have 1.2 squared times 0.2 plus 1.4 squared times 0.2. 1.6 squared times 0.2 plus 1.8 squared. If there were more than 5 of this is starting to get a bit tedious, right? Okay. However, using summation notation is more complicated because it's hard to write. But we're trying to get used to that. So if I type it right, I got 2.64. Again, back to my notes here. Each of these rectangles as an area, and I'm writing the area as height times base. The height of any one of these rectangles is its y value. The function tells me how to calculate the y value. So first I have to find the x values. Once I have those, I plug them into the function. That gives me the height, and then I multiply the base. So that's one rectangle, and then add for the next rectangle. We just keep repeating that over and over again. If there's 4, 5, 6 of them, not too bad. If there's 10, 20, 100, I don't want to do this anymore. I need a different method. Right? That's where the computer comes in. But to use the computer, you have to master summation notation, which is what we were warming up to in section 1. So in order to use summation notation, you have to see a pattern to the x values that you're plugging in. What did we repeatedly do for each x value here? We added 0.2. What's repeated addition? Multiplication, yeah. And we had to start at what number, though? Yeah, so starting at 1, we're repeatedly multiplying by 2. So new page. So my formula for the x values based on messing around there, they're called the x sub i's, or just xi's. Starting at 1, I want to add 0.2 repeatedly. How many times? I times. That's my variable here. So that is my formula for the x values. I need the height of each rectangle. The height of each rectangle is the y value. Y value comes from the function plugging in these x values. My function says take x and square it. So I have to square these things, the 1 plus 0.2 i's. So a Riemann sum is some sum of the function values times delta x. Then we have to figure out where to start at and where to end at. That can sometimes be tricky, but we've got that. So my function value I just calculated here. So I'm going to have the sum of 1 plus 0.2i parentheses squared. And what's my delta x here? Yeah, so I'm going to multiply this by 0.2. I chose my variable to be I here, so I is going to have to start somewhere and end somewhere. I'm just going to go back and double check that on my picture. On my picture, the initial point you start with, the 1, that's always called x0, the initial point, right? We started areas on the right side, which means our I starts with 1 this time. And it ended with 5, right? 1, 2, 3, 4, 5. I'm going to start at 1, end at 5. You're not sure why I'm making a big deal about that. You'll see when I do the left sum. So this is the summation notation. So on the quiz, I was asking you to draw me a picture of the function, draw a picture of the rectangles for the right sums that you're going to work on, calculate that, and show me the summation notation. The hardest part of all of that is coming up with the summation notation. So I have that right there. So let's do a left sum, and we'll compare the two. So I'll worry about typing that in the computer in a minute. So I'm doing 5 intervals, so homework will sometimes call this L5, the book calls it that too. That's an approximation for the area. And I'm going to put my sketch up here again so I can get an idea of what I'm doing. There's 1, there's 2, 1, 2, 3, 4. I'm going from here to there. So I'm still going 5 intervals, so 1, 2, 3, 4 divisions in there. But this time I want to start on the left side. So if I start on the left side, that means I'm starting with what we call x0. That's the left endpoint of 1. That one's always called x0. You can call it x1 if you want, but that's kind of not the convention. It doesn't matter too much. The next x value, how do I get to it? I add delta x, right? So if that's x0, the next one must be called x1, and that's going to be 1.2. Right? We already know that because we figured out what those are. X2 is going to be 1.4. X3 is going to be 1.6. X4, 1.8. Do I need an x5 here?
No.
No, right? I have 5 subintervals. I have 1, 2, 3, 4, 5 x values. From 0 to 4 is 5 years. Okay, what do I do with these x values next? Plug them into the function, then multiply by the width, and then add them all up. Okay, so new color here. So my L5 is going to be to take 1, plug it into my function, multiply by 0.2. Plus, take 1.2, plug it into my function, multiply by 0.2. Just like before, I just have a slightly different number to plug in each time. And then we just keep going. 1.4 squared times 0.2, 1.6 squared times 0.2, and 2, and finally 1.8 squared times 0.2. So it's always find the height, multiply by the base. Could you write base times height instead? Sure. But with Riemann sums, it's traditional to write height first and base. I'm going to plug that into a calculator and get an answer quick. We're going to try and do the summation notation next. And there's 2 different ways to do that. I'm going to use I as the variable again. What does it look like I should start I off at here?
0.
Yeah, this is kind of set up for me to start off with I equals 0. And then go up to 4. Right, so 0, 1, 2, 3, 4, that's 5 numbers. I just need five things. I got to then figure out what it is I'm squaring. Well, how did we generate these x values? We repeatedly added 0.2, right? Yeah, so will it work if I just go 1 plus 0.2 pi? Well, if I plug in 0 right there, what do I get? I get 1, that's cool. That's what I wanted. If I plug in 1, what am I going to get? 1.2, which is what I want. This looks like it works okay. So it turns out if I started at 0, pretty much the same formula, the summing as I had for the right endpoint works. I just tell it to start earlier in terms of counting. Multiply by your 0.2, these two things should match each other. And now where do we usually start counting at? We usually start counting at 1. So you'll sometimes see in solutions to these kinds of problems that the sum will start at 1, 2. I'm going to use let's use a k. I'm going to start k at 1. If I start at 1, I have to end at 5. Now, the problem I have when I use k equals 1 is that if I try to use the same trick I did before, if I plug in 1 here, I don't get the right left endpoint. I get 1.2 instead of 1.
Shouldn't that be?
So, what's that?
This is 0.2i.
That's supposed to be a 0.2i right there. So that doesn't
Wait,
work.
it's not a k?
Oh, k. That's what she's saying. Sorry, I got 2 U's for anything. 0.2k. If I plug in k equals 1, I get 1.2, not 1. Right? So if you really can't help yourself starting at 1, you got to alter this formula a touch. So what I do there is instead I just shift k here. So I put times parentheses k minus 1. Now, I don't like that because it looks way more complicated, but at least I get to start counting at 1. What happens if I plug in 1 here? What's 1 minus 1? 0. 0 times 0.2 is 0. I do get to start at 1 right there. So if you look in the book, you're going to see this formula usually for the left endpoint formula. And don't forget, we still have to multiply by our 0.2. So my preference is if I'm using right endpoints, I start counting at 1. If I'm using left endpoints, I start counting at 0, because then I get to use the same formula for this. Okay. I like that better. So you'll see this in the book. You might see this in some videos if you watch the videos. It's not my preference because I find this a little messier right there. But it turns out for any sum, there's more than one way to write the sum equation, depending on where you count.
Does it go for every sum equation?
Any sum equation can be written more than one way.
But like how the left endpoint and the right endpoint were the exact same, it just depended on where you count. Yeah. Is that true for every function?
Yes. Okay. If you do what's called a regular partition, and a regular partition means they're always the same space apart.
Okay.
Yeah. You can, in calculus, have an irregular partition in a Riemann sum. And there was a homework example where your table jumped by like 11 and 4 and 6.
There's like a 57.
Yeah. But usually we try to stick with regular partitions because they're easier to work. So 2 different options. This first one is my recommendation right there. Okay, so we are going to take this a step farther than the quiz. So I think I got the main ideas from the quiz. Let me look at the quiz here for a sec. See what other questions might pop up. Oh, I remember a question somebody asked. I stated something that was viewed as confusing. Here I say the interval is from 1 to 2, but down here I say sketch the interval on 0 to 3. The reason was, how many people look at their graphing calculator and then put that on paper to make a graph? Everybody raise your hand. Right? You all do that, don't you? Okay. I often, because I've seen these functions so many times before, I kind of remember them and I just plot a couple of points and rough it. So my fear was that if I didn't say only graph from 0 to 3, that you would whip out your graphing calculator and you would type like f of x equals 1 over x was the function I asked you to graph, and you would draw all of this for me, and then you just have this little tiny space to draw in your rectangles there, right? Which would make it illegible. So I wanted you to zoom in just on this region right here. That's what I said that. Okay, so I should have just wrote, I'm writing this because I want you to zoom in on your picture, not have a picture that looks like this. because then I can't see the rectangles. It looks like a mess. Okay, so back here, let's see. Set up a Riemann sum with right endpoints. We did it. Use summation notation. We did it. Calculate that number and show the picture on the graph. For the second part, I didn't ask you to draw the left endpoints because otherwise you have to kind of redraw the picture. But I wanted you to eventually show the summation notation and evaluate it. When I do these, I always evaluate it by hand first and then try and come up with the summation notation because that helps me figure out if I'm right. Okay. So average those two numbers together was number 4, and then use technology for n equals 100. We're going to do that next. And then I'm going to take it one step farther. All right, onward and upward. So we're going to do the same problem, but with n equals 100. So f of x equals x squared. Interval is 1 to 2. N equals 100. We're not going to draw 100 rectangles by hand, right? That's crazy. I do need to know delta x. How do I find that again? Yeah, find the width of your interval, right? The distance from the left to the right. So that's just 1 divided by 100. That turns out to be a nice decimal, so you could go decimal or fraction, your call. All right. And I think I said use right-hand endpoints on this one. True. With right endpoints. Yep, cool. And usually I find right endpoints easier to set up. All right, so what's my first x value going to look like? Where do I start? I start at 1, then I add the 0.01, right? So yeah, it's going to be 1.01. So it's my starting value plus my delta x. What's the second x value? And sometimes by the time you get to the third one, you're like, oh shit, I see the pattern. Okay. So I'm just going to skip on down and say, okay, I need the variable I in here somewhere. So I'm going to say, I think I know how to do that. Can somebody help me write what the formula is for the i's one?
1 times I.
1 times I, almost.
1 plus.
1 plus.
0.01i.
0.01i, yeah. So it's the delta x that I'm repeatedly adding. So it turns out this is always going to be the case. The interval is usually said start at A and end at B. And so if we're using right endpoints, it's always going to be A plus delta x times I. Always going to work that way. Sometimes we get lucky and A is 0, but other times it's not. Like here, it's not. And so this is my x value, right? So I had to determine that. Now I need to determine the formula for a rectangle. Well, I need the height. How do I get the height? Plug it into the function, right? So the height for a rectangle is just going to be to take this x value and square it. So take that 1 plus 0.1i and square it.
Another 0.
What's that?
Drop the I and
Oh,
Another 0.
1.01. Shit, yes, you're right. Thank you. Who said that, Rob? Okay, so this should be 0, 1, and 0, 1 there. Okay, so that's the height. I want the area. What do I need next? The base. What's the base here? 0.01. Okay, so there's my base times height. So that's the height of the ith rectangle. What do I do next? I add them all up. How do you write add them all up? Yeah, use that summation notation. So I'm going to put sum up in front of that. I'm using I as my variable. Where should I start at for a right-hand endpoint? At 1. Where should it end at? In this case, 100. Okay. So now I'm going to show you how to plug that in 2 different ways into Geogebra. Turns out Desmos can do that too.
Wait, is there a difference? Is the summation sum like different from the squiggly? There's like
That thing right there?
no,
No?
it's more pointy. Is that the same thingy? Or is it
Yeah.
Yeah,
you mean
it's
as
hard to
sloppy.
draw.
Yes, yes.
So you want me to draw a meter like that?
No, I was wondering if those are the same thing.
They are the same thing. This is my fast
You're
version
trying
of
to
a
draw
sum.
a retort.
This is my slower, neater version of a sum. There we go. No, they're the same.
So that was it.
Good question. All right, so let's try and plug that into a piece of technology. So get your graphing thingy out, whatever it may be. And Geogebra is an app you can get on your calculator. It's not quite as easy to use.
On your calculator.
On your phone. A phone is a big calculator.
Okay, I was like, that's weird. A
Imagine-
calculator
imagine
inside your
your-
calculator?
Imagine your TI-84, but now another TI-84 is inside your TI-84.
And can do sums.
Well, before smartphones, I used TI-84s are programmable. So I used to write all kinds of programs on the TI-84. Like I wrote a program to do Riemann sums easier on the TI-84 a long time ago. Because that's what I do at night instead of watching movies.
Yeah, Chris.
Okay, so here's my function, right? I'm going in between 1 and 2, so I'm just going to zoom in a little there. And I'm going to do it first using the sum formula. So the way sums work in Geogebra, ooh, it's got the pretty version. Nice. So I just hit sum, enter in Geogebra. So I'm going to say I from 1 to 100. And then down here, I need an extra parentheses for my 1 plus 0.001. Oops, too many zeros that time. 0,
So you said sum and then
I just hit sum and enter. I didn't realize that worked.
I don't think
That didn't
That
work
doesn't
for
work
me.
on
It didn't work on a calculator.
Maybe
On a phone, I mean.
is that
A
a
phone, a
sig-
calculator.
Is that
She
sigma?
said it. She said it too. Okay.
That's sigma, right?
Does it work?
Yeah.
Okay.
What did you do sum?
I typed, let me get a new line. I typed the word sum and hit enter. Oh, it didn't do it that time.
Yeah.
So that's what I got.
How did I do that? I don't know.
Wait,
That's
what is
you.
it called?
Maybe I just
My
did.
phone crashed.
Oh no, let it out of the bag.
I don't know how I made that happen now.
Phone
Weird.
just crashed.
If you
What the
just
heck?
put refund and leave the fancy letter one down there.
Did you accidentally click down? Yeah. You click like a different one
So
instead.
like. with
Oh,
Just query givers.
it's down here somewhere?
No,
What do you
it's
say?
not.
How'd
In the, there's 3 bars, there's one that says number, and then
Oh, I
alphabetics, ABC, and then it's the Greek numbers. I think you can find it.
What?
You know, on the.
She's talking about right above the.
Oh, down here?
Yeah.
Yeah.
Somewhere? Or
Oh
over
yeah,
here?
you can, but it doesn't do it. Like it's not the
Yeah,
same.
it's not. It doesn't seem to work.
Because I tried that. How'd you
And
do
plus,
that?
it's weird.
Hey,
There's
look
like
back on the recording.
there's like 2 different epsilons.
I don't know. I can't make it happen again. So
Look
sorry.
back on the.
Okay. So otherwise, it works as you type your formula, which apparently I didn't finish here. I need parentheses around my x values. I need to square them and then multiply by 0.01. Okay. And I is my variable. Start at 1, go to 100. All right. Hit enter. I get 2.34835. So I'm going to write this down on my notes.
What's the interval again? 1 to 2.
From 1 to 2,
100.
yeah. So pretty print, I have I goes from 1 to 100 of 1 plus 0.01
Equals
I
expression.
squared times 0.01. In Geogebra, and I think Desmos is pretty similar, Geogebra, I type sum, and then my function times I squared times 0.01, comma, it wants to know what's my variable, it's I, where do I start and where do I end? So it's expression, comma, variable, comma, start, comma, end. And I go, was it 2.348 something?
2.34835.
2.34835.
I did E4. I got a different answer than that.
On the TI-84?
Wait, why'd you put 1 to 100 and not 1 to 2?
Well,
No, because this is the sum formula, and the sum wants to know how many rectangles I'm doing.
Okay, I was just wondering. 'cause
Yeah, that's different than the rectangle sum. That's a different function.
Okay.
What do we
Um,
do? Oh.
I think X is the problem here.
Oh, I have to do it.
I think you use a different variable because the calculator usually reserves X for other stuff.
You can use that.
I used X.
You used X and it worked on a TI?
Well, I was just doing it. Yeah, it works on. Yeah.
1 to 100 of 1 plus 100 times X times 100. Huh, that's bizarre.
Can we see it? Yeah, it's probably because the X has a value.
Yeah, so I just pick a different variable.
Sometimes if the number already, if the variable already has a value.
So just redo that with a different variable. Yeah, so on a TI, it lets you pick your variable, but on some TIs you can't pick X because it uses X for other stuff. Not on all TIs. It depends on the TI. Well, even TIs that look the same could have a different operating system in the background, only one server will be the same. Okay. Good. Do you have a calculator?
I have a laptop that you can get
Oh, yeah.
our decimals on.
Okay, have you tried it before?
Yeah,
Are you getting better at it?
yeah.
Okay, yeah, I just want to make sure everyone's comfortable with the calculating device. On the test, most of the tests you can use your calculator on, but there'll be a short part of the test that there's no calculator, kind of like before, where you have to do simpler examples. Like this, I could not do this couldn't be a non-calculator problem, right? You need a calculator to get the answer.
Maybe people look.
But there will be something like, hey, can you, by hand without a calculator, do 4 subintervals for me on this simple function? Okay, so we're going to take this one step farther. Does anybody else have a question about entering this? I'm going to show you the easy way now.
Mm-hmm.
Okay. So the easy way is to use Geogebra. Now, warning, you can't solely rely on this because then you'll miss some test questions if you don't learn how to write out your own summation notation. But in Geogebra, if you use the rectangle sum function, it's a little bit easier to work with. Because here, it just wants to know what is your function, where do you start at, like what value A are you using, where do you end at in your interval, what's your ending value, like your B value. And then if you're going to use a right-hand endpoint, which we often use, a 1 means right endpoint. Anybody remember what a left endpoint is? Yeah, 0 equals a left endpoint. Okay. So for the function we're working on here, I would just type x squared, start at 1, end at 2, give me right-hand endpoints. Oh, I'm missing something. I'm missing how many? That goes before the 1. So there's the n that goes before the 1, which is the number of rectangles. And this draws the picture for you too, which is kind of cool. So I'll demo that again. I used it the other day.
Wait, okay, so when you say f of x, what would be f of x in like that one?
Which number is that? Number 3? I'll do that problem in just a minute.
Okay.
Remind me after I do this. Let's see, so I'm going to do our rectangle sum, enter, and even though I can't see that part of it, I just type F and hit the right arrow, and it takes me into where I can see what's going on. Start value 1, end value is 2. How many rectangles do I want? 100. And 1 for the position of the number I plug in. And it draws all 100 rectangles, which looks like a mess there. And it says 2.34835, the number I got from the summation. Okay. So if in desperation the summation notation is not going well for you, you can check it with this slightly easier version of entering it. I don't think Desmos has that, but it's usually called a trapezoidal sum, which we might take a look at in chapter 3. We might come back and look at that.
For now, it's only focusing on.
Right now, we're just going to focus on rectangles because they're easier to work with. Yeah. All right, so I got a homework question. I'm going to come back to, yes, William.
It's still giving me the same thing if I pick like another pattern.
Okay, take a peek. Okay. After class, I will troubleshoot that with you. I'm not sure off the top of my head what's going wrong, but it's definitely making a big error there. And it's interesting, it's the same error each time. But what you wrote looks right. All right, so let me see. 1.2, number 3, is that right?
Yep.
Or 1.1, 1.2. So just a problem like this in reverse. Here is the Riemann sum. What I want to do, let's blow it up a bit. I want to figure out what function is being evaluated here. Okay, and the A and the B. So let me steal that into my screen. And I'm going to ignore the limit for the moment. Okay, so there's my sum, and the interval was from 3 to 6. All right, so in this case here, I've got a bunch of xi's, and I've got a 1 going on there, right? So, oh, it says xi star. Okay, so they're not worth, the star just means who cares whether it's left endpoint or right endpoint or midpoint. It's just some x value in the interval.
What would it look like if it wasn't
Is all that
right
means right there. What's that?
What would it look like if it was a right point? Like what would
If it was a right endpoint, then that xi, if it was a right, star just means who cares, it's any number. Xi would be starting at 3, jump by,
This is limit of n.
so this is just an n right there, so then delta x would be 3 over n times I.
So like they just wouldn't have the star.
And then I would have to multiply that by 2 pi. Yeah, so that would be right-hand endpoints. So this right here tells me that the function f of x, since they put a star there, you just replace it with a regular x. So the function must be 5 sine squared of 2 pi x plus 8.
That's your f of x.
That's the f of x. And this is starting at 3 and ending at 6.
So a would be.
So did I use this squiggle notation yesterday?
Yeah, you put a and
For the
b.
definite interval? Yeah. So this is what's called the definite integral. And your a goes at the bottom, so that would be starting at x equals 3. And some people write x equals, most people ignore the x there. I just like to put it in, but it's optional. End at 6, your function would be 5 sine squared, 2 pi x plus 8. That should go in parentheses, and then a dx goes next. That's the definite integral version of this when you take the limit as n goes to infinity. That's all.
Okay.
What's dx again?
Dx is like delta x. It's what the delta x turns into in the limit.
Which is the change of x.
Yeah, so let's see. There should be a delta x up here. Did I not copy that? It's just a change in x, yeah. Oh, they didn't even put it in there. Yeah, technically this is wrong. There should be a dx on the outside there, because this right here is just the height of each one. So I'll have to message whoever wrote this problem. There was a slight error in the presentation of it. And so technically that wouldn't work. There's an error there because they didn't multiply by delta x. This would be assuming delta x is 1, in which case it won't, the limit will not exist.
So do you know, like, so why did you learn the limit? So
If you take the limit of a sum, you get an integral.
okay, I see.
Yeah, so kind of like in Calc 1, when we took the limit of the difference quotient, it just turned into the derivative.
Okay, I see, yes.
Yeah. So that's the definition I gave the other day. So I'm just going to rewrite it. So if you take a Riemann sum, n equals, I, there we go, equals 1 to n of some function where you evaluate it at some x value in each interval. That's what the star means. Any x value in there, doesn't matter really. You multiply that by delta x because this gives you height times base. We need those little areas. So this is just going to give you an approximation. The bigger n is, the better the approximation. It turns out that you can sometimes take the limit as n goes to infinity of these things. And if you can evaluate that limit, if it exists, that's what we call the definite interval. Just like the limit of the difference quotient turned into derivative. And this would be from whatever a and b is of the function of dx. So this is equivalent to, in calculus 1, the limit as h goes to 0 of f of x plus h minus f of x over h. This turns into the derivative with respect to x of f of x. So would you agree from last term that this was very difficult, finding those limits, evaluating all that? It was hard. And eventually we found shortcut tricks, didn't we? Because at the end of the term, were we doing this anymore?
No.
No. We just knew the derivative of x squared is 2x, right? We had a trick that got us there. So our next goal, we don't want to have to make any more Riemann sums. They're wicked hard. We haven't even really taken the limit of any of them.
So
That's even harder.
So there is gonna.
So we're going to develop tricks so that we can go right to that. Yeah. Okay. So I was going to take the limit of that last function, x squared. Instead, I'm going to give you something new. I'll do that next week. All right.
Doesn't even.
Oops, that's not a pen. Pen. But it looks cool on the computer. I'm going to tell you right now a special trick called the fundamental theorem of calculus. All right, let's see which part do I want to do. I'll give you both parts. All right. So we got to start off with some function f of x on some interval a to b, and we want it to be continuous, unbroken, continuous. And then I'm going to make a function a of x that's equal to the definite integral. And let's see. Starting at a, going up to some value x. And I'm going to call the function f of t for a moment. And I'm going to put the variable as dt. So what does that mean?
Would it be a to t? That's a to x.
A to x. I'll show why. I'm going to draw a picture of what this means. Okay. So I have some function f of x. Let's say that's f of x. And this is a right here, and let's say b is way over here somewhere. So when I refer to the x value, x is some number inside that interval. So what does a Riemann sum do for us? Why were we using Riemann sums a minute ago? To calculate the area under the curve, yeah, right? So this right here is my area function. Because if you take the limit of a Riemann sum, you get what's called the definite integral. So the definite integral is, in a sense, an area function. So what this says is that area function, given that definition, finds the area up to whatever x value you tell it to go to. So if you told it to go from maybe 1 to 2, you get the area between 1 and 2. Okay, that's what that does right there. So that's not the theorem yet. This is the setup to the theorem. Here's what the theorem says. The theorem says is that if this is your area function, if you take the derivative of the area function, a prime, it's equal to the function you started with, f of x. What the hell does that mean? I'll explain that next.
Before it.
So what does derivative do? What did it tell us?
Slope function.
Slope. What's another phrase for slope? Not tangent line. Rate of change. Okay? A derivative says what's the rate of change of this function over time or over whatever x is. So a prime must be the rate of change of the area. How the area changes as x slides back and forth. Okay? Well, what's on the bottom of my area? Well, it's just a straight line, right? So the only thing that's causing this area to change is if x moves, the height changes. Where does the height come from?
F of x.
F of x. So all this says is that the way the area changes is dependent on the boundary at the top. This is the geometrical significance formula. So what? Who cares? Here's why I care. If you can take a derivative, can't you take an antiderivative?
Don't.
So
You can take an antiderivative. So it turns out antiderivatives are the cheat sheet for Riemann sums. So if I know how to take antiderivatives, I don't have to do Riemann sums anymore. Okay. So let me show you why. I'm going to take it one step further. So you're with me here, right? Doesn't the area change dependent on that top boundary?
Yes.
Isn't it obvious once I point that out? It's like, duh, yeah, right. I remember when my teacher first said that, I was like, so what? That sounds stupid. Here's the power of it, right? Check this out. So I have some area function, a of x, okay?
Do you really want to get started?
It's only going to take 1 minute.
Okay.
Here's a and here's b, right? Okay. So if I say what is a evaluated at b, wouldn't that be, so here's my function, wouldn't that be all of this stuff going back this way? And technically it actually can go all the way back to 0. Okay? Now, what if I say evaluate the area at A? Well, that would be this stuff over here, right?
Mm-hmm.
So if I say what is the area at B minus the area of A, shouldn't that be just the stuff left in the middle there?
Yeah.
Okay, so what that tells us is that if you take the antiderivative, let's switch to blue, from A to B of the function f of x, that is the boundary up here, then the answer is the antiderivative, which the area function happens to be, coincidentally, evaluated at the top point minus evaluated at the bottom point.
That's just.
So you have to like.
Okay, so quick, sorry, I know I'm keeping you over time, but check this out. A minute ago, we had f of x equals x squared from 1 to 2, right?
Yes.
Okay, what's an antiderivative for x squared? 1/3 x cubed. Okay, so if I wanted to find the area from 1 to 2 on x squared, I would just take that antiderivative and plug in a 2 minus the antiderivative, plug in a 1. Okay, what's 2 cubed?
8.
So if I take 8/3 and I subtract
1/3.
1/3, how many thirds do I get?
7/3. And that's
7/3. 3 goes into 7. How many times?
2 and
Twice.
2 and 1/3 left over, which is 2.33 repeating.
And that's.
1/3,
Oh, he did that in class.
which is what we were getting closer to with our rectangles, right? 5 intervals, we got 2.4 something. 100 intervals, we got 2.34 something. Oh, holy shit. Riemann sums began. We're not going to do any more of them.
Wait, really?
Okay, so we're going to spend the next 3 days on this, and we're going to review some more Riemann sums. If anyone needs another day on the Riemann sums stuff, I'll give you a late pass for free. I moved that due date from tonight to Sunday already. If anyone's behind. Woo! Man, I worked up a sweat there.